laser pointer here? Laser pointer. I have one in my office.
I can manage without it. I can use the mouse.
We have a laser pointer. Oh, okay.
If it's quick, then I grab one. But if it's not easy, don't worry about it. I can manage it. Thank you. So I'm kind of gauge the talk. So I'm gonna try to aim for about 45 minutes so that there's time for questions. But I can. It's not a problem. I can kind of make it go anywhere from about 35 minutes. I can actually make it go an hour. Probably with this group, not so much, because I would go into more detail about some more specialized optical design capabilities. Okay. I'll leave it there. I think we can start, and if you raise your laser pointer, that will be fine.
Okay. Hello, everyone. I'm Jie Qiao, a faculty here. Pleased to introduce today's speaker, David Hasenauer. And David is the Code 5 product manager from Synopsys. Synopsys is the umbrella company for a brand optical design company called Code 5. And David has been the product manager for a number of years. And he was actually from Rochester, from Penfield.
Penfield, yeah.
He went to University of Rochester and Institute of Optics and obtained his bachelor's degree in optics. And then he joined TI, heading up the optical design group. Worked for TI for a number of years. After that, he joined Code 5, has been engineering service and later product marketing division. So he's going to talk about the strength and different how to use Code 5 to achieve optical design efficiency and system performance. So just to acknowledge that Synopsys has donated 4 sets of software to RIT, including Code 5, that's the classical optical design software package. Also Light 2, where Amit is pursuing to show that to his class in radiometry. And the other 2 softwares are Beam Prop, is a traditional photonic design and integration software. And the 4th one is a grading soft, like you can design grading.
Yeah, so actually, our soft, which has Beam Prop and Grading Solve, has a number of packages. The actual 4th product that we have is called Lucid Shape, which is an automotive illumination package. But our soft has lots of stuff.
Yeah, we didn't ask. So
I see. I'm sorry, this is your program.
And lastly, I want to point out that David holds 6 US patents on the optical design aspect. So let's welcome his talk.
Well, thank you very much. I'm actually generally a very loud speaker. I can turn on the microphone, but is there anybody in the back who would prefer that I use the microphone? I prefer to be microphone free if I can be heard okay. All right. So this presentation, it's about Code 5, which is the classical optical design software for the development of imaging systems. And I understand that this is sort of adjacent to a lot of what you are doing. So I'm going to try to modify my talk a little bit to hit the higher points of things that you might be interested in terms of imaging science. But I do want to give you a flavor of what the software does for optical design, because even if you aren't doing optical design yourselves, as imaging experts in dealing with other folks in the world of optics, you may have to interface with an optical designer, and this will give you a sense of the tools and perhaps the way they think. Now this presentation, basically it has 2 sections. I'm going to talk a little bit about the software interface, so if you do happen to use one of the versions of, if you use Code 5, the program that we have donated to RIT, you'll want to understand a little bit of how the interface works. And then we'll talk about optimization and analysis items. And I'm going to do not only slides, not going to be a whole 35 or 40 minutes of PowerPoint. I'm going to do some live demonstrations in the software to illustrate some of these strengths. And this is really, it's not everything that Code 5 does. The amount of things Code 5 does is quite vast. but I want to point out and highlight some of those things that if you were to ask a customer that has access to Code 5 or ZMAX or Oslo, the other traditional optical softwares that are out there, why do they use Code 5? These are kind of the strengths, and so it gives you a sense of flavor for the strengths that we have. So first in our interface, fundamentally Code 5 is a command-driven program. We have a kind of a Windows standard interface in order to be able to not have to learn the 3-letter commands, of which there are many. But if you are an optical designer, you can get extremely efficient by putting things in on the command interface. And it's fairly interchangeable. You can do things in the GUI, or you can do things in the command line, and I'll show that in just a moment. We also, within the last 3 years, introduced a relatively new interface component, which is called Spec Builder. And among optical designers, pretty much all of our customers, this is very typical of how they work. And this may or may not be true for you as well. I kind of expect, in terms of engineering, that it is sort of a general truism. You're given your project requirements and goals, and so you've got either a spreadsheet or a Word document or some list of things that you're trying to achieve, and you really want to know if you achieve them or don't, because when you deliver your product, your design to the customer, they've got some must-haves, and they've got others that are goals or want-to-haves, and it's really important to know whether or not you've achieved that. And we developed an interface to kind of deal with that in a very nice way. So I'm going to actually skip the slides here. We'll go into Code 5, and I'll just show a little bit of the interface. So most classical optical design software is kind of a spreadsheet interface. Light Tools, which is our illumination package, is kind of more of a CAD interface. But traditionally, optical designers have kind of liked to work with information this way. If I have a lens system that's shown here, each one of these elements is represented by a front radius, a back radius, the thickness from one surface to another surface, and then what is the material inside the lens. And then you have the air spacing to the next surface, and so forth. And here I've just got lenses. They're all spherical surfaces, but you could easily have non-spherical surfaces. If I were to basically right-click on my interface and bring up surface properties, this is a sphere, but I could certainly change this to an aspheric surface, or QCOD. And now I have a number of other parameters that can be optimized or varied in order to try to improve the optical performance. If you think about the lens that's in your cell phone camera, pretty much everyone has a smartphone, I expect. If you think about the lens in that, those are 4 to 6 elements, and all of them, every surface is a non-spherical surface, because that's what it takes to get that to work in such a small, compact package. And so you have the ability to find these different surface shapes. And some of the surface shapes, kind of one of the areas, the research that is going on, RIT is a member of CFO, and so in terms of freeform surface shapes, these are surface shapes that really go beyond rotational symmetry and even beyond simple cylinders and toroids into using lots of parameters to define the surface in order to be able to make things perform better or be more compact. If I were to go into the system and basically I could come here and from the command line, just to show you in Code 5, I could say RDY S1 is 98, and if you look at the radius for surface 1 when I hit return, it turns to 98. I can do a Control Z to undo that. Similarly, I could just say that my thickness is 6, and then you'll see that there's a command down here. And so you can kind of do these things interchangeably in Code 5. Some software does not have a command entry, so other software does. It kind of depends on how old it is. But among designers who are using Code 5 3 days a week, 4 days a week, you can get incredibly efficient by using commands still. But pretty much everything can be done in the GUI. So the other thing that I want to point out, let me undo that change though so I don't mess things up, is this Spec Builder interface. And so if I were to basically go and say File, New Spec Builder, it brings up this blank interface, and I could go and click on these specs, and there's lots of different categories. There's system parameters, which are the first order parameters, things like field of view, etc. There's performance-based parameters. related to encircled energy, the concept of modulation transfer function, which you may or may not be familiar with, spot size, which I think most folks will be familiar with, but you've got these performance-based specifications, and then mechanical. In order to make these lenses or mirrors or whatever you have easy to fabricate, you might want to make sure that the aspect ratio, the diameter to center thickness, is a certain. If it gets too thin, it becomes hard to coat, it becomes hard to hold without distorting the surface. So there's all of these different specs, and I could add these manually one at a time, but that's going to be a little cumbersome for my demo. So I'm just going to delete that, and I'm going to open a pre-existing spec builder window. So let me just go to the open button, and I have a basically a spec builder window for this lens. Let me try to get some more real estate out here. And so what you can see, there's information about spectral range, effective focal length, some mechanical constraints. These labels are actually, I added those to show you which constraint category they came out of. There's even a thing called a user spec, where if I go and I edit that specification, I can use Code 5's macro language to define a specification that isn't one of our 55 or 60 built-in specifications. So pretty much anything Code 5 can calculate can become a spec. And the idea behind the spec builder window is that I have a lens. So if I bring up that view again, so I have this lens. These are the specifications. Some of them are display only. I just kind of want to know what the values are. Image clearance, I want that to be greater than or equal to 37.5 millimeters from the last lens to the sensor, whatever sensor that might be. Relative illumination, I'd like that to be greater than 60%. And then there's areas you can put notes if you have, these specs are coming from particular places. We also handle double byte characters. We have a lot of customers in Asia, and so you can put notes on these things. When I run Spec Evaluator, we'll actually loop through all of these specs, calculate what the values are. If it meets the goal or specification, it does not show up highlighted. If it misses, it shows up highlighted in red. Now, currently, I would have to manually go in and create an optimization set to basically modify this lens system in order to try to address all these specifications and goals. But I can imagine a future release of Code 5 where, based on communicating this information to Code 5, we can help you find a starting point and actually help you do the optimization more directly. But currently, it's still a manual process, so I have basically this optimization sequence of commands for optimizing that. So we're going to go and optimize that lens. You're going to see the lens change as it optimizes. Our optimizer is quite fast. It started with an error function of 352. I guess I could use a laser pointer, but this is not too high, I can reach that. So 352, that's based on the RMS spot size. If I take a point source like a star out at infinity and image it through the system, and I look at how big is just the geometrical spot based on tracing rays on axis at field 2, which is in green, and field 3, which off axis in blue, how big roughly is the RMS spot? This number is a representation of that. It's got kind of weird units, but it's a representation of the kind of average spot size in microns for across that field of view. That's our default error function. You can optimize on other things besides spot size, but that is by default what you get. And then you can see it pops up primarily as it tries to grab some of these goals and constraints where things are missing. But then it drops back down, so now it's below in terms of spot size where it was. Hopefully with these constraints held, and so forth and so on until it gets to the end. It's down to a spot size that's about maybe a fourth or a fifth of what it was. This is how the error function changed in every cycle, and it did a tolerance analysis. I won't talk about that so much. If I go and run Spec Evaluator again, you can see that everything, if I scroll through this, everything is met except for this one spec, which is the MTF, which is a measure of performance. It's the average over all the fields, and we're just a little below the specification of 50%. And if I were to look at the results, I can actually look at the details, and what we see is that for the on-axis field, the MTF is actually really good, the off-axis fields is where I'm kind of losing it. And as an optical designer, the first thing I would try is to redo my optimization and weight the off-axis fields higher and the on-axis fields lower. But a lot of good information in there. But this is a very typical way for an optical designer to work, and it's kind of a nice interface to let you quickly make sure that your design is, you don't miss something, essentially. Okay. And I'm going to just skip the slides associated with the demo. Now, in terms of optimization, one of the chief purposes of having optical design software is to have it automatically optimize. Fortunately, the days of having to kind of do all this manually, that was, gosh, now probably about 75 years ago. So computers have been on the scene for a long time, and in fact, even before Code 5 was released as a product, it was being used internally at Optical Research Associates, Code 1, in fact, used internally starting in about 1963. So it was right around the late 1950s, early 1960s, that for imaging optical design problems, optimization started to kind of show itself, and you didn't have to do manual stuff. Code 5 has a very powerful local and global optimizer, and I'll explain the difference between those two if you don't know what they mean a little bit later. We've got some expert tools as well. So Optical Research Associates, the original company that made Code 5, and which is now part of Synopsys, we have always had an engineering services team. When I first joined ORA, I wasn't dealing with the software side of the business. I was on the engineering team just using Code 5 to solve problem for external customers. And so the benefit of that is that we've got a lot of engineering knowledge. And what we've tried to do with these expert tools is to build the engineering knowledge into the software so that you get better designs, even if you don't have that much experience with optical design and engineering. And then we have a very specialized feature called optimization for alignment, which is a way in which in the lab, if you have a misaligned optical system, you can take interferometric measurements for various field points for that system, feed that into Code 5 directly, and Code 5 can compute an alignment solution so that you can correct the misalignments in your system. And there are some installations of Code 5 that are purely for this. They're in a lab helping customers with these off-axis mirror systems align them in about a fifth of the time that they were able to do so manually. So let me just see here. Okay. Yeah, I'll talk a little bit, and I generally like to put a few more pictures in my presentations. But there's two types of optimization. One is called local optimization, and the other is called global optimization. If you think of a solution space, an n-dimensional space, and we're just going to deal with 2 dimensions because it's easier, as a topology. What a optimization is that based on the different parameters, the different variables, in the case of a 2-dimensional space, we're really just talking about 2 parameters. So as you think about a lens system that might have 100 variables, your 100-dimensional space, is if you think of a 2-dimensional space, I can change those 2 parameters through a continuous range of variables such that some will have a really much better spot size performance and others much worse. If I sit essentially, basically think of it as mountains and valleys. If I sit on the side of a mountain, what I want to do is to change the parameters to get to the bottom of a valley. That is a smaller spot size, which generally is better, and that is what local optimization is all about. I'm sitting on the side of a mountain. There may be more than one valley below me, but local optimization always goes downhill, and it goes to the bottom of the valley. Now, it doesn't really care if that valley is really close or if that valley is really deep. It just wants to go downhill and get to the bottom of the valley really quickly. Global optimization instead basically says, I want to find all the valleys. I want to find all the valleys that I can see, and then I also want to head up the mountain and look to see if there's valleys on the other side. And so we have some fairly strong features for both local optimization and global optimization. Yes?
So these problems are generally non-convex problems. You have different minimum or different locations you have to search for?
You do. I mean, so you generally have so the question was, I missed actually the first part, but you have different minima and different locations that you're trying to search for. It's generally a continuous space, and you're starting at a non-optimum location. And then again, local optimization just tries to get to a minima, but you have a continuous space with minima, no really maxima so much, but with many, many different minima based on different configurations. Yeah, and it's that the dimensions of the space really depend on the number of variables that you have. So with global optimization, again, it can go and find values that you can't even see. One of the reasons that the Code 5 optimizer is strong is that it has really strong constraint handling. For a lot of software, they tell you, add the constraints just like they were an aberration. So I'm optimizing on spot size, but if I want to have a lens that has an effective focal length of 50 millimeters, well, we'll target that to 50 millimeters, we'll add a weight to it, and now that's part of the solution space. When you add constraints to the merit function that's performance-based, two things happen. One, you're increasing the dimensionality of the solution space, so you're making the solution space more complex. And two is you might not be able to get there exactly because you're trading off spot size versus this focal length you need. Usually, if a camera manufacturer wants to have a 50 millimeter focal length, they want that to be 50.000. And we have a method of handling constraints exactly called Lagrange multipliers that essentially separates the handling of the constraints from the damp least squares process that we use for local optimization. And it works really, really well in our software. It's something that the founder of our company, who started Code 5, figured out back in the late 60s. And that's one of the reasons we optimize to better solutions faster than some of our competitors. Given that we've traditionally been the most expensive software out there for doing this, it's the reason why we're still in business. You know, we've had a lot of lower cost competitors, but they didn't optimize as well. And also, we'll talk about tolerancy in just a bit. So I actually want to go and just jump and do an example of that before I get that, which is this example. So let me go into Code 5 again. I'm just going to get rid of our spec builder window here. And I'm going to run, it's kind of a canned optimization example, but the optimization you're seeing is running real time. So if you have used software, you'll get a sense of the speed that Code 5 optimizes. It tends to be faster than what our competitors do. And this is going to run fast enough that I'm going to let it run, and then I'll explain what it just did. So it's going to run really fast. And it's done. So let me go ahead and blow that up here. So here's the problem. I've got a space-based system. A lot of the systems that you are designing the instrumentation for and other things are going to be space-based. Unobscured reflectors are really nice and space-based. You put an obscuration, you get diffraction effects and reduction of contrast. So we want to make this into an unobscured reflector. But what you can see right now is we're pretty far from it. This mirror is completely in the way of the incoming beam. This mirror is also in the way of the incoming beam. We can't even get raised past some of these mirrors in order to get to the final image, which actually is on here. It's a little hard to even see it. It's yeah, right up here. Yeah, so it's in bad shape. So via exact constraint handling, I'm going to set up constraints in the optimization sequence that is just going to basically do algebra. It's going to treat these rays, so which are representations of photons coming in, as lines. And it's going to treat where these rays either hit a surface as a point, or if I've got two rays that are crossing, like at a stop or a pupil, I might want to treat that as a point. And I'm just going to set up all these algebraic equations, which you can do very easily in Code 5, to say, hey, I want to keep this point below this incoming line. I want to keep the point, and by the way, the fact that it seems to be going into the surface now, these are rays that are in and outside the plane. So you're seeing a cross-section in the plane of the paper, or the screen, and then these rays, the surface actually comes out there, and it comes in. So that's a tilted reflector that's causing that. So, but I want to basically keep points out of the way of the lines. And you can set up a really easy, compact set of constraints to do that. And when I do that, if I go now, you can look at, here are the before optimization spots, pretty big. And here's the starting optimization. It's got a merit function of 90,000, which again is kind of a representation of the blur spot sizes across the field. and we got all these lenses in the way. In 1-2 cycles of optimization, all the clearances are met. Now it's showing you the parent part. We're going to eventually chop off the unused part of these optics that we don't need. But what you can see is that where these two rays cross are below that line, where this ray hits this point is above this line, where these two rays cross is below that line, and where the ray hits this surface is below that line. And so we have essentially put, within 2 cycles of optimization, have all the clearances. Now the beauty of exact constraint handling is that as long as things don't try to encroach, they don't influence the error function at all. And so now Code 5 can optimize in the least constrained mode to get to a really good blur spot solution. And so we can kind of see as the system changes, these are all cycles of optimization. So after about 32 cycles of optimization, or 30 cycles I guess, error function started really big, about 90,000, and basically settled out down here. We can lop off those unused portions of the optics, so we don't need these other portions, and we have a completely unobscured system. And if we look at those spot diagrams, here's the after optimization spots, and here's the before. And this is the exact constraint handling is kind of one of the big things with the Code 5 optimizer that works really well. There are certain constraints. If you have a parameter that varies in a nonlinear fashion, I should say a very nonlinear fashion, versus a variable change, those actually do better if you add them to the error function and weight them. Otherwise, they can bounce around in the optimizer. But for many, many kinds of constraints, including those clearances, being able to use that exact constraint handling works quite well. I think I'm going to skip a little bit of it in the interest of time. And so another significant feature strength is glass selection. And this is an expert tool where one of our engineers, Dr. John Rogers, and our engineering team, is an expert in figuring out glass choices in order to optimize and get a better performing design, especially in terms of chromatic correction. And what Glass Expert does, it's a glass substitution, and it basically goes through and you give it a list of materials, either from Schott or O'Hara or what have you, germanium, other materials, and it will go through and do substitution and figure out the best glass combination for your systems. I'm just going to mention it. I'm not going to spend so much time on it. If there's anything, so again, if you are starting to use Code 5 and you have a particular problem, my contact information will be here. So please just contact me if there's something in particular, more detail that you want. I'd be very happy to help you through it. But I'm going to kind of skip that. We have a similar expert tool for aspheric surface placement. So in this example that I had before, which was the Tessar, where's Code 5? There we go. So let me go ahead and restore this initial lens that I had, this wide angle lens. So in this example, let's say that I could allow 1 or 2 or 3 of these surfaces to be non-spherical and try to help the performance. What would be the best surfaces to choose? Now, optical designers very often have kind of this like, oh, we should put 1 near the stop in order to control pupil aberrations, and then maybe 1 away from the stop in order to control aberrations with field. And that's a pretty good rule of thumb. But what Asphere Expert does, it actually goes through in a very fast computation. It's not trying every single one. In about the time it takes to do that first cycle of optimization, whether you have 10 surfaces or 800 surfaces, it can rank all the surfaces in terms of where is an A-sphere the most leveraged, where's the next most leveraged A-sphere, and so forth and so on. And so it can very, very quickly tell you in a very complex lens where A-spheres would will give you the best improvement in performance. And so again, we're harnessing our engineering knowledge in order to provide some functionality that you just won't find with software that doesn't actually have an engineering team working with it as well. Now, global optimization, gosh, I wish that they had given a picture. We've got a very nice picture that shows sort of a 2D topology. And in fact, I'm just going to find that really quick. I am watching my time, but let me just escape for a moment. And let me just go to my presentations. want to bring up this picture because I think this will help understand topology a little bit better. So this is a classic two-dimensional problem, which means we can plot out the error function space. I've got a error space doublet. The two red curvatures are variable. And I can plot how does the error function change, which is based on spot size, based on changing the curvature of surface 2 and the curvature of surface 3. And this is a really interesting example that was provided to us from Delphi University. If I start with these 4 systems, almost the same curvature on surface 2, but slightly different, very slightly different curvatures on surface 3, they optimize into one of 4 local minima that we have here. So every step is downhill. There's like a really weak local minimum here, and it gets down. So this is showing every optimization step, how it finds a local minima. And so local optimization basically always has to go downhill, and as long as it gets to one of these minima, it's good. Global optimization, in this case, you can't, it's only 2 parameters, so there's no valleys on either side, but you could imagine that I might be sitting at the bottom of this valley. Local optimization would never get me out of there. Global optimization would find these other valleys as well. And so that kind of gives you a nice illustration for global optimization. It's trying to find all of these minima that are in solution space, which, as you add variables, becomes a very large n-dimensional problem. So I hope that was a useful graphic too. And I'll probably make a note to add that to this presentation we have here. So our global optimization works quite well, but we also have a very fast method of analyzing the impact of tolerances on optical performance. And because we generally people are using our software to build systems that are going to be fabricated, you really want to kind of know how, am I going to be able to meet the performance after we apply reasonable manufacturing tolerances? Because of this very fast method, and that's going to be the last thing I'm going to demonstrate, well, gosh, okay, I want to watch my time here. I'm going to wrap up in 10 minutes, I promise. Because we have this fast method of tolerancing, we can actually build that into the optimizer. And if we were to look at a global optimization, here is the optimization error function. So this is based on spot size. And this is the as-built RMS wavefront error. So not the nominal RMS wavefront error. So if my optimization was on the RMS wavefront error, getting smaller would mean that I've got better RMS performance. But this is the as-built. So we've applied a set of tolerances to all the parameters in the system. And this would be a perfect correlation if this was just the nominal RMS, because it's going to be correlated to the optimization function. But when you put in the as-built, what you find is that some systems that have a really small nominal error, when you add tolerances, become a big error. Other systems, this one has 3 times worse in terms of its nominal error, but it's the best in terms of the as-built performance. And in order to kind of get these better designs that have good fabricated performance, what you want to do is communicate generally to the global optimizer, which has the freedom to change the form significantly of the lens or mirror system. You want to communicate that you're interested in the as-built performance. And we have 2 methods of doing that. I'm not going to, this is really more deeper into optical design. I'm not going to dive into the details, but here is the same optimization, what gave me this system before, where I've added one of these 2 methods, this SAB method. And now all the solutions are, 1, have good as-built performance. You've got this really great correlation between as-built performance and merit function. And you're not wasting time finding all these solutions that you don't really care about. And also, many of these solutions are better than the best we got when we didn't tell Code 5, hey, worry about as-built performance. So that's another feature strength that we have, is that our tolerancing method is so fast that you can do this very effectively as part of the optimizer. And I'm not going to demonstrate that because of time. I'm going to skip that one as well. I think really what I want to do is I want to do a quick demonstration of our tolerancing, and I want to finish up with what I think may be one of the features that you would find most useful too, BSP, beam synthesis propagation, a beam propagator, and then also just a little bit about image simulation. So, okay, let me do that. So I'm just going to, I'm just going to jump to beam synthesis propagation, I think. We have a very fast tolerance, so let me just say that. So generally Code 5 is doing ray-based type of analysis. We do a diffraction analysis for some things, like to get a point spread function, but the way we generally do that is we trace rays up to the exit pupil of the optical system, do a fast Fourier transform, and that basically gives us the image structure in the focal plane. Sometimes, though, you really need to just propagate the wavefront through the entire optical system. There's lots of different methods to do this, and we have one method that was actually developed to solve a problem that NASA had that the commercial beam propagators that were available at the time, it's about 2006 or so, couldn't solve. And it was for the terrestrial planet finder mission. They were trying to directly image a terrestrial Earth-like planet around a nearby star within about 50 to 70 light years. The difference in magnitude between the star and the planet is going to be about 10 to 12 orders of magnitude. And the way they're going to do this is they're going to take a space-based telescope with a coronagraph arrangement, so they're going to block the light of the star and then try to directly image the planet. The diffraction of light from the obscuration just swamps out the signal. And so what you have to do is, or at least what NASA was doing with this one project, is applying these apodization filters in order to suppress the noise floor so that basically 10 order of magnitude planet can pop up above the noise floor and be directly imaged. And so beam synthesis propagation allowed them to essentially achieve this result, and compared to the tools that were currently available, they had calculated to be about a 1-year computation time. With beam synthesis propagation was about 3 weeks. For many problems, beam synthesis propagation can do the analysis in seconds. But it's a very nice method if you need to do generalized beam propagation to look at diffraction effects in your optical systems, gratings, what have you. You can use this feature. And so here's an example of a dispersive singlet. We're looking off axis, and we are deliberately making this from a very dispersive material. And if I look at the spot at the image plane for the red wavelength, the green wavelength, and the blue, I can look at those individually. And we can also do a incoherent summation of those intensities to see the intensity distribution for the polychromatic spot. And so, again, you can see kind of the red, the green, and blue. The colors here don't correspond to the colors of the spectrum. They correspond to intensity. But we have the ability to do either a monochromatic or polychromatic analysis. We can do polarization studies. So here we have a diverging beam through cross polarizers. This is without polarization ray tracing turned on, so we see no effect. We turn on the polarization ray tracing, and you get the characteristic Maltese cross effect, which, because of the fact that the electric field vectors for this diverging beam, the angle that they make with the cross polarizer transmission axes allows a little bit of bleed through. And you can see here, this is like e to the -3, this is e to the -9 or something like that. So it's a very small amount of energy, but you can essentially do an accurate polarization analysis. And you can even look at the X, Y, Z, radial or azimuthal components. So if you are working with polarization studies, beam synthesis propagation can help you there. And then the last thing, and I will finish with this, is image simulation. So you are doing a lot with your imaging sciences. So what we do have is a feature in Code 5 to help let designers, or in particular designers, communicate with folks who don't really understand optics. They don't know what an MTF curve is or a spot diagram. It's a way of communicating the performance of the optical system. It allows you to put a bitmap at the bitmap picture, if you will, at the object plane, and then analyze the distortion effects and the aberration effects at your sensor plane. And so here's an example. We have the Hubble Space Telescope. And when we do an image simulation result based on the original conic, which was a wrong value, they had made a mistake, and it was a wrong value, you basically, with this input galaxy, you get this. When you use the correct conic, it basically reproduces what the input image was in this case. You can compare this, however, to this is the actual image through the Hubble. The main difference, the main error in this result is that there is some information out here that was below the threshold that the detector could detect, and so you don't see it. But if you look at the blurring of the stars here and kind of the group up here, it matches really quite well. And so image simulation allows you to simulate what the optical performance through your optical system. And we also have a large number of macro functions that allow you to manipulate these image simulation results. If you wanted to basically add veiling glare, or you could basically work on things on a pixel by pixel basis in the Code 5 macro. You could also export that information to MATLAB and do work in there and then bring that in. So there's lots of different ways if you want to do further post-processing. But what this feature is doing essentially is it creates a point spread function map across the format of the object, and then essentially does a convolution of every pixel with the point spread function. We don't need, even if we have a very high density image, we can do a linear interpolation between the point spread functions we have to synthesize point spread functions based on just a linear interpolation of all the values in the grid in order to synthesize them to get faster performance, a little less accurate, but faster calculation time. And we also support mapping. Instead of mapping that object simply kind of by rectilinear mapping, we can also use orthographic or stereoscopic. So, and that's needed if you have like a hyperhemispherical field of view system like this. Here's kind of a hyperhemispherical wide angle. This is an iPhone camera panorama, which uses equal angle mapping. And so here we kind of see, for this lens system, how that system would be distorted on its sensor plane and blurred out based on mapping that object in equi-angle space as opposed to a rectilinear space. Okay, so 45 minutes. I think I'll stop there. I hope this gave you a nice overview, and I realize, again, this is really geared to the optical designer, and you're using optics mostly for the imaging analysis and things, but I do believe that there probably are some things, such as image simulation and the beam synthesis propagation, that you might find useful for your own work. And I will say is, learning how to design a lens is really good for job security. So that's something that I kind of highly recommend you play with it a little bit, because that's something that optical designers can get jobs pretty much anywhere. Thank you very much. Are there any questions that I can answer for you?
Questions? Question. So the optimization for alignment feature, does that work well for high precision alignment, or is that more, you mentioned like in a laboratory environment that you needed to do like, premier telescope assemblies, something like that?
Yeah, so the question is on the alignment feature for that we have, is it like for kind of high precision alignment, versus the alignment of the kind of systems I mentioned. So essentially, I'll explain what it does, and then that hopefully will answer the question. So with this very fast tolerancing method that we have, we know how changes to the exopupil function affect a subset of performance metrics, such as RMS wavefront error or diffraction MTF. So what the alignment option does is that you set up a model in Code 5 that represents your optical system perfectly aligned, but kind of in the alignment, however you're getting your interferogram. So your kind of as measured configuration, which may be different than your as used configuration. Code 5 then analyzes it, and it knows what the exopupils for your perfectly aligned system, what the exopupil functions should be. Now you go and use an interferometer to get the phase and amplitude information for the different fields for your misaligned system. And then Code 5 can very quickly calculate, okay, You then tell it also, here are the parameters that I'm going to compensate with. Code 5 can very quickly tell you, okay, if you move those parameters by this much, and this much, it is going to get your perturbed, misaligned exit pupil functions to match as closely as possible to the perfectly aligned. Sometimes it helps if you do it in multiple stages, so you'll do one stage if you're pretty far out. You put in those adjustments, you do it again, new interferograms, and that will get you closer. So you can sometimes do it in multiple stages. But it is it's really sort of meant for macroscopic, large, or I should say large optics, but optics that are being aligned in quantity in order to kind of help with cutting down the time it takes to do alignment via other methods, like looking at the interferograms and tweaking the knobs. It tells you what you have to tweak. Yeah.
Are these licenses, like, so we're going to have access to, are they virtual or are they going to be on specific desktops?
The goal is to be on the server, and our IT support, Brett, is setting it up. So you can actually email him directly if you want to use it. Even if it's not on the server, I think he can help you to install on the desktop.
Yeah, we do. So because it's a little easier to manage, we are very happy to give out license on the server. But we're actually, if you have a need, we can basically give you a license that will be tied to the PC, and you just fill out a license agreement. So that's something we're very happy to do. So if you want to have Code 5 on your own personal PC, we can manage. We can arrange that. And Light Tools and the other software that you have as well.
One question is shift and variance in systems. I believe that there are no shift and variance systems. Do you have any way of modeling how shift and variant, or what is the aplanatic patch generated by the imaging systems that you can design here? Is that a metric you can?
We do have a way. So basically, and I forget the reference for this, but if we have a system where, and I think of this like an optical designer, so my terminology may be a little different than yours. If you have a system where the offense against the sign condition, so you're kind of moving away from the aplanatic condition, is large enough, and I forget exactly whose calculation we're doing, but it means that the character of the airy disk changes over about a 12 airy disk size. We put out a warning, and if you have that situation of where you have so much coma in your system that you can't really rely on predictions like the modulation transfer function, which is really for extended objects, we kind of warn you about that. In terms of the point spread function, I don't know that we don't warn you. I mean, it just says if you have a point-like object, this is where the point is. We are predicting what it's going to look like. But if that point-like object over a very small aerial region of the image can change character enough, we basically have warnings related to that. And that's usually if you've got a system with a lot of coma. But I'm not positive I answered your
yeah, well,
question.
That's a good answer.
Okay.
Yeah, thanks.
Yeah.
And also, you're doing the beamlets. I guess they're Gaussian beamlets, as opposed to actually doing Fresnel propagation through the system.
Yeah. So we are. It is a beamlet-based method, and in as much it's most similar to Gaussian beam decomposition. We don't actually disclose the nature of our beamlets, and the reason is this: is that when we basically did this for JPL, when it was first developed. The best propagator out there was ASAP, which was Gaussian beam decomposition. That was the one that would take about a year to run. The big problem was the way that they were going to be able to see this planet was with apodization filters. And the three problems with Gaussian beam decomposition is if you hit an aperture and you clip the Gaussian, then you lose accuracy. If you have phase variations across the beamlet, so it's no longer a Gaussian phase, you lose accuracy. And if you have transmission variations across the beamlet, which is the problem they really had, you lose accuracy. Now the way you solve this with Gaussian beam decomposition is you make smaller and smaller beamlets, but smaller and smaller beamlets spread faster, so you have to resample more frequently in order to get all the beamlets through the system. And so it was just a really problematic. So what BSP does, and again, we don't disclose what the beamlets actually are or kind of how we do this, but with far fewer beamlets, with in fact, I can show a very quick example. A graph, I think, will show this better. Let me escape that. Go back to, should have this, BSP. Let me just scroll all the way to the appendix. So essentially the simple approach, that's essentially Gaussian beam decomposition. And so here what we have is, this is just something we calculate theoretical. Plane wave, circular aperture, and basically perfect imaging. What do we have in terms of the ring diffraction ring structure? So the black represents, all the way up to ring 60, the normalized irradiance and radial position of the diffraction pattern. The area disk is just this little thing right there. That's to the first dark ring. So if you use with about 5,000 beamlets Gaussian beam decomposition, it holds up really well, out through about ring 5. Now you're starting to see, it's a very small error, but you're starting to see a little difference in intensity. Then you start to see a shift where the bright rings are where the dark rings should be relative to the black. But it's sort of this gradual degradation in the performance. One thing with beam synthesis propagation, it actually has this feature called pre-analysis, which will actually figure out the inputs for you to get an accurate answer. It works about, I'd say, 80 to 85% of the time. And one of the things it needs, one of the pieces of information it needs is how big of an area at the image do I care about? And it's going to make different recommendations for the inputs based on that. So with the beam synthesis propagation method, if I go with the 5,000 beamlets, okay, it actually is this blue curve. And what its characteristic is, it's just perfect out here to about ring 24, and then it falls off quickly. And then if I wanted to say, let me cut that computation time in half, so I'm going to use about half the number of beamlets, and now I'm saying I only really care in terms of the, the green one went up to ring 40. That was that 5,000 beamlets. If I only care out to about 0.03 or 0.04, I could use half the number of beamlets. And you can see that the simple approach is pretty degraded by that point, whereas beam synthesis propagation's doing really well. So you tell it how big of an image patch you're interested in, and it can do the analysis with far fewer beamlets. And that's really what caught NASA's eye, because it, again, took about what would have been a year computation time down to 3 weeks. And then, of course, the program became unfunded, and but then we turned it into a feature for all of our customers, which was nice.
Thank you.
You're welcome.
So how long will that take?
Well, this example is fast. So the 3-week versus the 1 year, that was the terrestrial plan finder with these very fancy appenizations. I did an example in the lab actually earlier for one of your PhD students where I did an example like on a ball lens that took a second. So there's lots of stuff here that can be quite fast. I mean, if I can do a very quick, I can do a 5-minute demonstration if you'd like to see it.
Oh, maybe.
Yeah.
We can do that individually.
Okay, we'll do that after.
Any other questions? Oh, so do you use machine learning for design? I actually recently reviewed a paper. The authors use machine learning to determine the misalignment from freeform instrumentation.
Yes. So the question is, would you use machine learning for our software? I will say not yet, but it is something that we are really interested in. So to kind of go back to our roots, optical research. This is an area that we're kind of researching and looking into. So there's a lot of kind of very interesting things coming out of an optimization theory, such as flock behavior, that's not the right word, swarm behavior optimization, and some really interesting papers that are coming out. And so these are things we're researching because if they are things we can implement and offer advantages in some situations, it's something we certainly want to be on top of. But we don't have machine learning at this time.
So our students, actually, some of them like to do machine learning on everything.
Oh,
So
okay.
it could be a good collaboration opportunity if you're interested in this area of research.
Okay, cool. Yeah.
Okay, so without further questions, let's thank our speaker again. We have a reception outside.
Okay. Thank you.